In section 15.4, we learned about Green's theorem, which was a means of computing line integrals via double integration. In 15.7, we're going to talk about the divergence theorem, and that's going to enable us to compute flux, which is normally defined as a surface integral in terms of a triple integral. So before we get started, let's talk about a couple of terms that we'll need here. Recall from the previous section that a two-sided surface is said to be orientable, and a one-sided surface is said to be non-orientable. So if you'll recall, we gave an example of a two-sided surface. We had drawn the sphere. Another common two-sided surface would be a plane. Right? So there's clearly one side and the other on a plane and also a sphere. One-sided surfaces are less common. The one we talked about in the previous section was the Mobius strip. Another common example is the Klein bottle. All right, so we're going to focus on strictly orientable surfaces. So we have notation. Let sigma represent an orientable surface, so it can be thought of as having a positive and a negative side that has a unit normal vector, n, at each point. All right, so let's just draw a quick schematic diagram here. I'm going to draw an upward normal, give it a name n. And I'm going to let this be a normal vector on a piece of a plane. So here's a patch of a plane. And then we can also have a downward normal. And we would denote that with negative n. All right. So we're always talking about orientable surfaces with a positive and a negative side where we can attach this unit normal vector at every single point on the surface. All right, informally, the flux of an incompressible fluid moving freely through a permeable surface can be thought of as the volume of fluid that passes through the surface in 1 unit of time. Now, suppose that the velocity of the fluid at a point xyz on the surface sigma is given by this vector field F with component functions lowercase f, g, and h, all functions of xyz. And suppose that n is the unit normal toward the positive side of sigma. So I'm emphasizing their positive. Then the flux of F across sigma, denoted with the Greek letter capital phi, is given by phi equals the surface integral over sigma of F dot n ds. All right, so this entire definition was given in the previous section, section 15.6, when we talked about applications of surface integrals and flux. Please refer to that video for more discussion on flux and how it can be interpreted. So our focus in this section is how to compute flux, but without using surface integrals. So before we get there, we have a couple more definitions. First, surfaces that are the boundaries of finite solids are said to be closed, okay? So finite solids, just meaning that we have finite volume, right? Surfaces that consist of finitely many smooth surfaces joined together at the edges are piecewise smooth. Furthermore, we have a definition. Certain surfaces can be assigned an inward orientation, which is an orientation toward the interior of the solid, or an outward orientation, which is an orientation away from the interior of the solid. So let's draw a schematic diagram of a closed piecewise smooth surface with an outward orientation. You could just draw a sphere, which would be very smooth, but let's actually draw a box here. So first I'm going to sketch the box. So here's the front face of the box, and I'm going to make it fairly square. And I'll also indicate the back of the box here. All right, so we can see that this is a closed surface because it's bounding a finite amount of volume. It's also piecewise smooth because each of these 6 planes are smooth planes, and then they're joined together at edges. So this is a closed piecewise smooth surface. And then what I'm going to do is at the middle of each of the faces, I can define my outward normals in this manner. Okay, and then of course there would also be one in the back. All right, so this is a box, which is closed and piecewise smooth. With outward orientation. All right. So before we state our main theorem, let's just recall how to compute the divergence of a vector field. The divergence of F is the partial of the first component function F with respect to X, plus the partial of the second component function G with respect to Y, plus the partial of the third component function H with respect to Z. I like to recall that this can be written as the del operator dotted with F. And the reason why I like that is because we need to remember that the dot product outputs a scalar. So divergence inputs a vector field and outputs a scalar expression. I say it over and over again, but it's so important in Calc 3 to remember what your output is. Are you working with a scalar or a vector? So I shouldn't see any I hat, J hat, K hats, or angle bracket notation when we're working with divergence, right? This is a scalar expression. All right, so now the main theorem of this section, the divergence theorem, let G be a solid whose surface sigma is oriented outward. If F is a vector field where F, G, and H have continuous first partial derivatives on some open set containing your solid G, and if N is the outward unit normal on your surface sigma, then the flux, which is normally expressed as the surface integral of F dot N ds, can instead be expressed as the triple integral over the region G, or I should say the solid G, of the divergence of F dV. In other words, the outward flux of a vector field across a closed surface is equal to the triple integral of the divergence over the region enclosed by the surface. All right, so it's super important here to just recall what the hypotheses are that we're using. So we're talking about a surface that is oriented outward. We have continuous first partials, and we're working with a closed surface. So as long as these things are holding, we can apply the divergence theorem to forego the surface integral and instead compute the triple integral. Here again, when we're working with triple integrals, sky's the limit on which coordinate system you want to use. So take a look at what your region or your solid G is and decide, is rectangular coordinates going to be easier? Should I use cylindrical or perhaps spherical? So we'll see examples of using various coordinate systems here in this section. All right, one quick remark before we get into our first example. It says the divergence theorem is also referred to as Gauss's theorem. So look, Gauss was like this superstar in mathematics. And if we called every theorem that Gauss came up Gauss's theorem, then there would be like a million Gauss's theorem. So I just wanted to bring to your attention that at times, yes, the divergence theorem is called Gauss's theorem, but there are so many other theorems that are also called Gauss's theorem that I'll always refer to it as the divergence theorem. All right, so for our first example here, use the divergence theorem to find the flux of F across the surface sigma with an outward orientation. So we have our vector field, which is X, Y, and Z in each component. Sigma is the surface of the solid bounded by the paraboloid Z equals 1 minus X squared minus Y squared, and the XY plane. So what I'd like to do first is just sketch this solid. So I'll draw my rectangular coordinate system. Make sure to label your axes. And this paraboloid has been flipped downward and shifted up 1 on the z-axis. So it's going to come down and around, and then it stopped at the YZ plane. And so I just want to make a note here that when z equals 0, which is the XY plane, we get 0 equals 1 minus x squared minus y squared, or in other words, x squared plus y squared equals 1. So this is the unit circle here in the XY plane. All right, so I'm going to note here that this is a closed piecewise smooth solid. All right, and we can just say here by looking at a glance that our vector field has continuous first order partials. X, Y, and Z all have partials of 1 or 0, so we're good there. So we can apply the divergence theorem. So that says that the flux can be represented as a triple integral over our solid G of the divergence of F. So first I want to take the partial of the first component function with respect to x, which gives me 1. Then I want to add it to the partial of y with respect to y, which is 1, plus the partial of z with respect to z, which is also 1. And then I have dv here. So we can see that instead of computing the surface integral, we're just integrating the constant 3. At this point, we need to decide which coordinate system is going to be best. Since we can see that the projection into the XY plane is a circle, that's indicative that we either want to use spherical or cylindrical. Here, cylindrical is going to be best because we don't have a common radius. So if this were a hemisphere, we would want to use spherical. But since this is a piece of a paraboloid, cylindrical is going to be our best bet. So let's go ahead and set this up. So what I'm going to do first is I'm going to transform my integrand, and then I'll go ahead and fill in my limits of integration. So I have 3, and then dv gets transformed to r dz dr d theta, and we still need to determine our limits of integration. So for theta, we want that entire paraboloid. So we want to go 360 degrees, 0 to 2 pi. For our radius, we want to go 0 to 1. And then for our z limits, we want to find the upper and lower bounding surface. The lower bounding surface is z equals 0, right? The xy plane. The upper bounding surface is z equals 1 minus x squared minus y squared. And in cylindrical coordinates, that's 1 minus r squared. And then just fill everything back in for your integrand and differentials. All right, so we're ready to integrate. So first I'm going to integrate with respect to z. That's going to pop out as z. I'm going to just go ahead and plug in that upper limit of integration though. I'll skip that step in between. So this is going to be 3r times 1 minus r squared. Of course, plugging in the lower limit of integration gives 0, so I won't even plug that in. Next, let's go ahead and just distribute inside our integral. So this is a 3r minus 3r cubed dr d theta. So we'll integrate with respect to r. That's going to give me a 3/2 r squared minus a 3/4 r to the 4th, where r is running from 0 to 1. So I get the integral from 0 to 2 pi of 3/2 minus 3/4 d theta. All right, so 3/2 minus 3/4, that's 6/4 minus 3/4 gives me 3/4. And then when I integrate with respect to theta, it just kicks out a theta from 0 to 2 pi. So my final answer here is 3 pi halves. So this is the flux of this vector field across the surface sigma. All right, let's do one more example of utilizing the divergence theorem. Number 16, we have our vector field F as stated. Sigma is the surface of the solid bounded above by z equals that positive square root and below by the xy plane. So hopefully at this point, you guys have had enough experience working with these types of functions to recognize that this is an upper hemisphere with radius A. So let's go ahead and sketch this. So here's X, Y, and Z. So this is going out A on the y-axis, A on the x-axis, and A on the z-axis. Here, since we're working with a solid that's a sphere, it's pretty clear that we'll want to use spherical coordinates. So when we get to that point, we'll go ahead and set that up. But I'll just go ahead and note that this solid is closed and it's also piecewise smooth. All right, we also have continuous first order partials for our vector field. So just making sure that we can apply the divergence theorem here. So let's go ahead and set it up. The flux of this vector field across this surface is going to be the triple integral of the divergence of F. So first, let's take a look at the first component function, which is 2xz. I want to take the partial with respect to x. So that's going to give me a 2z. Next partial, I want to take the partial of yz with respect to y. That's going to give me a z. And then finally, the partial of z squared with respect to z is 2z. So everything here is in terms of z's. All right, so of course, all of this is going to simplify to a 5z. And then we also discussed that we want to set up our triple integral in spherical coordinates. So let's go ahead and set that up. I'll come back to my limits of integration here. Instead of a 5z, I'm going to write it as 5, and then remember z is a rho cosine phi. And then dv in spherical coordinates becomes a rho squared sine phi. And then the order of the differentials is d rho, d phi, d theta. All right, so for our rho limits, our radius is running from 0 to a. Phi, remember, is the angle that you're moving from the positive z-axis. So since we're only going from z down to the xy plane, that's 90 degrees or pi over 2. So 0 to pi over 2. And then theta is the angle we want to sweep around in the xy plane. So since we want that entire hemisphere, we want to go from 0 to 2 pi. All right, so we have everything set up. We can begin by integrating with respect to rho. Keep in mind that we actually have rho cubed here. Now, if you want, you can pull your 5 out front. That's a personal preference. I'll rewrite my outer two integrals. And then the integral of rho cubed is a 1/4 rho to the 4th, where rho is ranging from 0 to a. And then I still have my cosine phi, sine phi, d phi, d theta. All right. So we know that we're going to plug in a for rho, and that's all just going to be a constant. So I'll just pull that out in front for the next step, 5/4 a to the 4th. And then to integrate with respect to phi, I'm going to do a u substitution. Let's let u be sine of phi. Du is going to be cosine phi d phi. And we see that exactly here. So it's going to be a direct substitution. And then it's up to you as to whether you want to change your limits of integration. I'm going to rewrite the 0 to 2 pi, but I'm going to go ahead and change it. So here where I see a 0, I'm going to plug it in over for the u equation. Sine of 0 is 0, so that's going to stay the same. And then I also want to plug in pi halves for phi. So sine of pi halves is going to be 1. So my limits of integration are going to switch from 0 to pi halves to 0 to 1. And then when I substitute, I get u du d theta. And here again, I'm not going to ever resubstitute back for phi. So when I integrate with respect to u, I'm going to get a 1/2 u squared. Whoops, that's an a to the 4th. Integral 0 to pi, 1/2 u squared, where u is ranging from 0 to 1 d theta. And so that's just going to give me a 1/2. So I have 5/8 a to the 4th integral from 0 to 2 pi of d theta. And so that's just going to pop out a theta from 0 to 2 pi. And so my final answer here is going to be, cancel out a 2 everywhere, 5/4 a to the 4th pi. All right, and so this is the flux of F across that hemisphere there. All right, so we've seen a couple of examples of computing flux via the divergence theorem. Next, we want to talk a little bit about sinks and sources. So we have a definition here. If P naught is a point in an incompressible fluid, and if the divergence of the vector field F at P naught is positive, then the flux across G is positive for a small sphere G centered at P naught. So this is telling us what's happening nearby the point P naught at which we're evaluating our divergence. So this means that there's a greater volume of fluid going out through G than coming in. All right. So they're just telling you how to interpret a positive flux, that a greater volume is going out than coming in. Such points at which the divergence is positive are called sources. Conversely, if your divergence is negative, then your flux is negative, and those points are called sinks. So that means that there is a smaller volume of fluid going out than coming in. So basically, you're having kind of a backup, right? I like to think of sinks and sources in terms of rivers. So we know that a source of a river is essentially where a spring is beginning. So water is coming up from the ground or wherever it may be originating. And then you can think of a sink as like a river delta. So for example, at the bottom of the Mississippi River there in the Gulf would be considered a sink, right? That's where a lot of the flow of the river ends. It brings a lot of the sediment with it. And so less is coming in and a lot is going out. So let's draw a little schematic here. What would a source look like? So you can think of this as where things are emanating from. So I have a point here, and then I'm just going to draw some vectors pointing away, but emanating from that point. So I'll label this as a source. And then a sink is going to be the exact opposite. This is where vectors are going to head towards or converge inward. All right, so source, you emanate out, sink, you come in. Now, if the divergence at a point happens to be 0, then we just say that that point P naught is neither a source nor a sink. So let's end this section by determining whether some points are sinks or sources. All right, so determine if F is free of sources and sinks, and if not, locate them, meaning locate where the sources and sinks are. So what we want to do is we want to start by computing the divergence of F. All right, so just as a reminder, this is going to be the partial with respect to x of the first component function plus the partial with respect to y of the second component function plus the partial with respect to z of the third component function. So what we get out here is y minus x plus 0. All right, so how do we interpret this? So right now I have the divergence just at any particular point. You might even want to write this as the divergence of f at any particular x, y, z is y minus x. All right, so we can note here that the divergence is 0 when y equals x. All right, so for points of the form x, x, z, where the x and y coordinates are equal, those are neither sinks nor source. So I'm just going to make a note, neither a sink nor a source at points of the form x, x, z. Okay? But if we have points other than that, they are either sinks or sources. So I'll just note here that the divergence of F is going to be positive when y is greater than x. And so I'll just note that these are going to be sources, and the divergence of F is negative when x is greater than y, in which case we call these sinks. All right, so we have divided 3 space into those 3 sets, neither sinks nor sources. Those are all points that are lying on the plane y equals x. And then on one side of the plane is sources, on the other side of the plane is sinks. So let's do the same here for 36. Let's start by computing the divergence. All right, so first, the partial of the first component function with respect to x is 3x squared minus 1. The partial of the second component function is 3y squared minus 1. And the third component function is 3z squared minus 1. All right, so let me just rewrite this. This is, if I collect all of the squared terms, I could factor out a 3, x squared plus y squared plus z squared, and then of course minus 3. All right, so I'll just make a note here that the divergence is equal to 0 when 3 times x squared plus y squared plus z squared equals 3, or in other words, when x squared plus y squared plus z squared is 1. So let me correct that y there, it got a little crazy. So we have neither sinks nor sources on the unit sphere centered at the origin. All right, but inside the sphere or outside the sphere is either going to be sinks or sources. So we're going to have sources whenever x squared plus y squared plus z squared is greater than 1. In other words, when that radius is larger than 1. So outside the sphere. And we're going to have sinks whenever x squared plus y squared plus z squared is less than 1. So that's going to be inside the unit sphere. All right, so just by looking at the divergence here, we can identify whether a given point is going to be a sink, a source, or neither. All right, this concludes our notes over the divergence theorem.